Okay, in this video we're going to start section 6.4, and that is going to be the graphs of the sine and cosine functions. So today we're going to cover these first two bullet points, sketching the graph of the basic sine and cosine functions, and then we're going to explore changing the amplitude and period of these sine and cosine functions and how those change what the graph looks like. In the later videos, we will sketch translations of the graphs of sine and cosine, and then finally use these sine and cosine functions to help us model real-life data. Earlier, when we first started talking about the unit circle, we had our xy plane and a circle of radius 1. And then we wrapped the number line around the unit circle. So say here is a point on the unit circle that corresponded with, say, a 60-degree angle. Our sine value here was the square root of 3 over 2. As we did another lap around the circle, our next lap around would take us to 420 degrees, and that had the exact same value, square root of 3 over 2, for the sine function. And as we kept wrapping the unit or the number line around the circle over and over, every lap we would return to this sine value. So what we're going to do today is sort of unwrap the number line from around the unit circle. So on our graph now, our y-axis is going to go from -1 to 1. That was the range of sine and cosine. And now when we unwrap it, we are going to have the radian measure on the x-axis. So maybe here's pi radians, here's 2 pi radians, 3 pi, 4 pi, and so on, 5 pi. Remember, we had 2 pi was a trip around the unit circle. So something's going to happen in the graph here to 2 pi, and then it's going to repeat to 4 pi, and repeat to 6 pi, and repeat forever after that. That's why these are called periodic functions. So let's see what this looks like when we unwrap the unit circle. Here is our unit circle. We are going to start with the sine function. Remember, sine is the same thing as the y value on the unit circle. And remember, sine starts at the origin. Sine starts here at a y value of 0, and it's going to start out by increasing. So our sine graph here is going to start at the origin of the xy axis, and it's going to roll out in a wave. So here we're starting at the origin. Our y values are increasing. We're coming up to the top of this hill. Now we've maxed out, and we're headed back downhill. Our y values are decreasing. We're getting close to the the x-axis. Now we're in negative y territory. So we're down here. We're coming to the bottom of a valley. We bottom out at 3/2 pi, and we start working our way back up. And here is 6.28 is 2 pi radians, and we're done. So there is the sine wave. And I like to say that sine starts at the origin, or right on the x-axis. 2 pi later, it ends on the x-axis, and right in the middle, it crosses the x-axis again. We start by going uphill. We hit a peak at a 1/2 pi radians. That's the top of the unit circle. And then we go downhill, cross the x-axis. We bottom out in the bottom of this valley. That corresponds to 3/2 pi radians, where our y value is at its lowest, -1. From there, we start to increase back up until we hit the point that we started, right on the x-axis. So that's the sine wave. Cosine is very similar. But cosine, remember, cosine is our x-coordinate. When we start, our x-coordinate on the unit circle is 1, so our cosine graph is going to start up here at 1 on our y-axis. And why is the graph not showing up? Let's hide sine. Oh, there it is. Okay, now this is the cosine function. It'll loop back around. Here our x value is -1, and now we're heading back up. Here our x value is 0, so we're crossing the x-axis, and now we're headed up to a peak. And this will finish. It'll come back around here. Ooh. Start that again. Here we start up at the 1 on the y-axis, and we start going downhill. Okay, now we have them both graphed there at the same time. The green is the sine wave. The red is the cosine wave. They're actually identical to each other. One has just been shifted over to the left or right. Again, where sine started at the origin on the x-axis, it ended on the x-axis 2 pi radians later. Here, the cosine wave starts at the top of this hill at y is 1. 2 pi radians later, it's going to end at the top of a hill. Right in between the peaks of those hills is the bottom of a valley, right at pi radians, 3.14. In between the top of the hill and the bottom of the valley, we cross the x-axis. Same thing here, between the bottom of this valley and the top of this hill, we have crossed the x-axis. So there are the very basic sine and cosine waves. The green one is y equals the sine of x. The red one is y equals the cosine of x. And that's what we're going to have here in this text. In this section, you're going to study techniques for sketching the graphs of sine and cosine. The graph of the sine function is a sine curve. In the figure, the black portion of the graph represents one period of the function and is called one cycle of the sine curve. The gray portion of the graph indicates that the basic sine curve repeats indefinitely in the positive and negative directions. The graph of the cosine function is shown in the next figure. Recall from the previous section that the domain of sine and cosine is the set of all real numbers. In here, that's our x-axis, measured in radians. Moreover, the range of each function is the interval from -1 to 1, and each function has a period of 2 pi. Do you see how this information is consistent with the basic graphs? So again, here's our period of 2 pi. The graph starts at the origin, does a hill, crosses the x-axis down to a valley, and back up. And we're right back where we started. We have completed one full cycle, one hill and one valley, and then that will repeat every 2 pi for infinity to the positive x-axis, and the same to the left, to the negative on the x-axis. So here on the top is the sine wave, and below it is the cosine wave. Again, cosine, I like to say, starts at the top of a hill. 2 pi later, it ends at the top of another hill. In between the hills, right below, the middle is the bottom of a valley. So the hill starts at 0 and the valley is at pi radians. Halfway in between, we cross the x-axis. Same thing from the bottom of this valley to the top of this hill, right in between is 3/2 pi radians, and that's where we cross the x-axis. The sine wave starts at the origin. 2 pi later, it ends at the same place. Right in between those x-axis intercepts is another one. So first we start out with a hill. We peak out at 1/2 pi radians, and then we head downhill. Then we go into negative territory, down to the bottom of a valley at 3/2 pi radians, and then we start going back up to the x-axis. To sketch the graphs of these basic sine and cosine function by hand, it helps to make notice of 5 key points in each period of the graph: the intercepts, the max points or the top of the hills, and the min points, the bottom of the valleys. So sine starts out at the origin, and then we have our first hill a quarter period later, whatever the period is. Again, for the most basic graph, it's 2 pi. A half period, we're halfway done with the graph. We have completed one hill and we're crossing an intercept of the x-axis. From there, we're heading downhill. 3/4 of the period later, we are at the bottom of a valley, and then we come back up and we finish where we started on the x-axis, and we're about to keep going back uphill. One full period for 2 pi. Same for the cosine function. We start at a max, or at the top of a hill. A quarter period later, we have an x-intercept. Another quarter period later, we're at the bottom of a valley. Another quarter period, we're back to another intercept. And then the final quarter period, we're back to our maximum, or at the top of a hill, and then the cycle repeats. So here in example 1, it says, using key points to sketch a sine curve. Sketch the graph of y equals 2 sine x on the interval from -pi to 4 pi. Now what the heck is this 2 going to do to the graph of the sine wave? Let's see here. Oops. Sine wave. Here is the basic sine wave. It goes from 1 to -1 and has our period of 2 pi starting at the origin. Now the red one is just simply sine of x. I'm going to hit this button, and we now have a blue one, which is the full function. And what we have right here in front of sine, this number a, we can change by using this slider bar. Right now it's set at about 1. As I drag the slider bar, that's going to change this number. Right now it is 1 sine of x. What happens if it's 2 sine of x? Well, right about there is almost 2 sine x. What we did is increase the amplitude. We used to have our peaks and valleys running between 1 and -1. Now our peaks and valleys run between 2 and -2 because this a value here is now a 2. What if I make it bigger? 3 sine x. We're just making our hills higher and our valleys lower. We can go below 1. Here again is 1 sine x. What if we make it a half sine x? Here's a half sine x. Our hills aren't as high. Our valleys aren't as low. You know, and we can make that smaller and smaller until we just about flatten the sine wave out. Now what happens if we go negative? This is 1 sine x. What about -1 sine x? If I change that to a -1, the hills and valleys have been reversed. We're used to sine starting at the origin and going uphill, like the red curve shows. But if it's a -1 sine x, we're going to start at the origin, but instead of heading off to a hill first, we're going to go down into a valley. Everything else is still the same. So a coefficient in front of sine, a positive coefficient makes our hills and valleys higher or lower. A negative number flips it. It's almost like a mirror image. And the same is true for cosine. The green line is our cosine function, y equals the cos of x. Here is the full function, and again we have a letter a in front of cosine. As I make that bigger, that's 1 cosine x. Here's 2 cosine x. Here's 3.5. Here's 4 cosine x. That just stretches our hills and valleys higher and lower. And that is the amplitude of our function. So, when we're graphing this, we're used to having our peaks and valleys, our highs and lows from 1 to -1. But now we got a 2 here. So our highs, our peaks are going to be as high as 2, and our valleys will be as low as -2. You know, this distance here is our amplitude, A. Here we can go up 2 from the x-axis. Here we can go down 2 from the x-axis. And we're not just going to graph one period of this. We're going to graph from -pi to 4 pi. So let's see, I'm going to come out here and I'm going to make this 4 pi. And just by eyeball, I'm going to cut it in half. Here's about 2 pi. And I'll chop this interval in half, you know, from 0 to 2. Half of that is 1 pi. And then in between 2 pi and 4 pi would be 3 pi. And I'm not going to write them in, but, you know, we can chop those intervals into half. Here would be 1/2, 1, 1.5, 2, 2.5, 3, 3.5, 4. And I'm also going to do that to the negative side. Here would be -1 pi. Now we want to graph the sine wave with our hills as high as 2 and our valleys as low as -2. So sine starts at the origin. 2 pi later, we've completed a full cycle. 2 pi after that, we've completed another cycle. So we know we're going to be crossing the x-axis at these points. Also, in between the start of the period and the end of the period, the sine wave crosses the x-axis again. So we are going to cross at pi, and in between 2 pi and 4 pi, we're going to cross again at 3 pi. And on the negative side, we're going to cross at -pi. The blue dots are the x-intercepts. And in between the x-intercepts are our peaks and valleys. I'll use black for that. Remember, sine starts out going uphill. So in between these intercepts, we're going to have the top of a hill right up here, above 1/2 pi. So we're going to go up, come down, hit this intercept again. Then we're going to go down into a valley between pi and 2 pi. The bottom of that valley will be right here, below 3/2 pi. And then we're going to start going back up. In between 2 and 3 pi, we're going to have another hill that peaks out at 2.5 pi at a height of 2. And then back down to a valley here at -2 below 3.5 pi. And the same will occur on the other side. We'll cover that after we sketch in the graph that we have so far. So sine starts at the origin. We go up to a hill. We hit our hill at 2. And then we start heading down, cross the x-axis at pi, down into negative territory. Bottom of the valley, back up, cross the x-axis at 2 pi. There is one full cycle. We've done a hill, cross the x-axis, done a valley, and we're back to where we started. And then the cycle continues. Back up, another hill, down, cross the x-axis, bottom of a valley, back up. So right there are 2 periods of the sine function of 2 sine x. And we also got to go back to the left. We got to go to negative pi here. So if we're following this, we're going downhill. We'll continue down, bottom of a valley, down a little here, and then back up. So there is the graph y equals 2 sine x from negative pi to 4 pi. Again, that 2 is just our amplitude. How high and low do our peaks and valleys go? So in the remainder of this section, you're going to study the graphic effect of each of the constants a, b, c, and d in the equations in the forms of, this is the one we already looked at, a times sine of something and a times cosine of something. That just is our amplitude. It stretches it up and down. And we'll explore the rest of these variables one at a time. The constant factor a in this is the scaling factor, or a vertical stretch or vertical shrink of the basic curve. If the absolute value is greater than 1, the sine curve is stretched. If the absolute value is less than 1, if it's a fraction or a decimal, we shrink the curve. The hills aren't as high, the valleys aren't as low. The result is that the graph of y equals a sine x ranges between negative a and positive a, instead of negative and positive 1. The absolute value of a is called the amplitude of the function. The range of the function y equals a sine x for all a values greater than 0 is from negative a to positive a. And in the blue box is the official definition of amplitude. The amplitude of a sine x and a cos x represents half the distance between the min and the max values of the function. And it's given by amplitude is the absolute value of a. So here in example 2, scaling, vertical, shrinking, and stretching. On the same set of coordinate axes, sketch and graph each function. And here we have the cosine function. Cosine has a period of 2 pi, so I'm going to come out here. This will be my end 2 pi. In between 0 and 2 pi, halfway point would be 1 pi. And then we'll chop those intervals into halves also. So here's half pi. And here is 3/2 pi. And those are the radian measure of the actual coordinate axes in the xy plane. In part B, we're going to have an amplitude of 3, and in part A, we're going to have an amplitude of 1/2. Okay, so since our maximum amplitude of these two functions is 3, I know that here on the y-axis, I'm going to go from a positive 3 to a negative 3. When we graph letter B. And for part A, our amplitude is just 1/2. Now this isn't really going to be to scale, but let's put right about here 1/2, and right about here negative 1/2. So I'll graph the first one here in red. So the cosine function, remember, starts at the top of a hill. So here for cosine, we're going to start here at positive 1/2. 2 pi later, we're going to end at the same place we started. In between, these are the peaks of hills. In between the peaks of these hills, exactly in the middle, is going to be the bottom of a valley. So here in between 0 and 2 pi is 1 pi, and that is going to be the bottom of a valley. In between the first peak and valley, we will have an x-intercept. And in between the bottom of the valley and the peak of the next hill, we're going to have an x-intercept. So there's our 5 key points. If we start here at 1/2, we're going to head downhill until we x-intercept, down into negative territory, hit the bottom of this valley at pi radians, and then start working our way back up, cross the x-axis again at 3/2 pi, and then back up to end on a hill just like where we started. For the second one, part B, y equals 3 cos x. The only difference is now our amplitude is 3. So here, this cosine function is going to start at 3, top of a hill, also end at the top of the hill, 2 pi radians later. In between the peaks of these hills, right in the middle, is pi radians, and that's going to be the bottom of our valley. In between the peaks and the valleys, we will cross the x-axis in the same spot that the first function did. So there's our 5 key points. 3 cos x starts here on this hill, goes down, crosses the x-axis exactly where the first function did, and then we're down into our deeper valley. And then we start our journey back up, cross the x-axis, same spot, and we're back up into positive territory, and we end at the top of a hill. Again, 2 pi is our period of the cosine function. So there we can get an idea of what those numbers do. The 1/2 cos x and the 3 cos x, it just stretches the graph up or shrinks it down. You know, if we were to graph the regular old y equals the cos of x, 1 cos x, you know, that would be right about here, and we would have our same x-axis intercepts. So we know from a previous section that y equals negative f of x is a reflection in the x-axis of the graph. And we went over this with that geometer sketchpad thing. You know, the first one, the light gray one, is 3 cos x, because again, cos starts at a hill, ends 2 pi later on a hill, and has a valley in between. If we change that to a negative 3 cos x, this negative 3 cos x, the negative 3 means we start in the bottom of a valley. 2 pi later will end in the bottom of another valley, and in between those valleys is going to be the top of a hill. And we'd have our x-intercepts in between. And what we've just done is sort of reflected that like a mirror image across the x-axis. Now the period. Remember, the period of the basic sine and cosine functions run from 0 to 2 pi radians. We can change that by playing with another one of those variables in the parent function. Let b be a positive real number. So we have a sine of b times x, or y equals a cos of b times x. To find the period of the function, you know, the usual period is 2 pi. Whatever numbers in front of x, you know, that this b represents, we are going to just divide that into 2 pi. And let's see if we have something about that in the Sketchpad program here. Let's go back to sine. We're going to turn this back to +1. So what we're going to do is play with this b number. Right now this is the sine of 1x. What if we have the sine of 2x? Well, here's sine 2x. It's sort of scrunching it up like an accordion. Here would be the sine of 3x. We're making it a tighter wave pattern. The waves come quicker. This would be sine of 4x. Again, our period becomes shorter. And we can also do that in the other direction. Here again is sine of 1x. What if we did the sine of a half x? Here's 0.5x. We're stretching it out. You know, the waves are becoming longer. And the same thing would happen for cosine. Put this back to our parent function. And this is the cosine of 1x. Well, here's the cos of 2x. The cos of 3x. The cos of 7.5x. You know, as we increase that number in front of the x that we're taking the cosine of, we scrunch that up, make it quicker and quicker waves. And the same thing if we go below 1. Here's again 1x. What about a half x? Or 0.2x. We're making those waves come longer and longer. It says, note that if b is between 0 and 1, the period is greater than 2 pi. It's going to take more than 2 pi radians to get our full cycle. It's a horizontal stretching. Similarly, if b is greater than 1, the period is less than 2 pi. We're used to doing one full cycle in 2 pi. Well, if we increase that number, we might have a full cycle in 1 pi. We might do a hill and a valley and get back to where we started in 1 pi instead of 2 pi radians. That's a horizontal shrinking of the graph. So I think it's easier to see. I'm going to rewrite this function as y equals the sine of 1/2 x. I think that's easier to see than x divided by 2. These are exactly the same. Y equals the sine of a half x. Well, to find the period, we take 2 pi and divide it by this coefficient. So I'm going to bring this 1/2 over here. 2 pi divided by 1/2. Well, 2 divided by 1/2 is 4, and we still have our pi. So now the period of this graph, the period is 4 pi instead of 2 pi. So now I want to graph this, and I'm going to have a period of 4 pi instead. The coefficient in front of sine is a 1. You know, it's implied. So I know my hills will be as high as 1. My valleys will be as low as -1. And now instead of having one full cycle in 2 pi radians, it's going to be 4 pi. So I'm going to come out here. This will be 4 pi. Halfway in between 0 and 4 pi is 2 pi. And then between 0 and 2 pi is 1 pi. And between 2 and 4 is 3 pi. We're dealing with the sine wave, so that starts at the origin. 4 pi later, we're done with a full cycle. So we're going to end here. In between the starting and ending point, we will have an x-intercept at 2 pi. And remember, sine starts out by going uphill. So in between 0 and 2 pi, we're going to have the peak of a hill above 1 pi. And then between the x-intercept and the end, we're going to have a valley down here below 3 pi. So there are the 5 critical points to the graph. Sine starts at the origin. It's positive sine x, so we're going to go up. We're going to hit a hill at 1 pi. And we're going to come back down, and we're going to cross the x-axis at 2 pi. And then we're going to continue down into a valley, and then back up, and we're going to end at 4 pi. If I wanted to compare this to the original, y equals sine x. You know, here in blue, this is y equals the sine of a half x. In red, I'll graph y equals sine x. And we're used to having sine start at the origin and have a full cycle done by 2 pi. And have an x-intercept right in the middle. So we'd go up, have our hill, come back down, go into our valley, come back up. In red is sine of x. In blue is the sine of a half x. We've just stretched it out. We've made it take longer to complete one full cycle of the sine wave. Okay, here are 3 huddle problems. You know, pause the video, try these problems, come back, start the video, and see how you did. Okay, let's see. For number 6, it says find the period and the amplitude. Well, remember the period, or this is 3 cos of 2x. So the amplitude, that's just how high do the hills go, how low do the valleys go. We just see some numbers down here on the negative y-axis. We got a -2 and a -3. It looks like the bottom of our valleys go from -3, and the top of our hills would go 1, 2, 3. So our amplitude looks like 3. You know, that's the distance from the x-axis to the top of a hill, and also the x-axis to the bottom of a valley. So our amplitude is 3. What is the period? Well, usually the cosine function has a period of 2 pi. But because we have this 2 here, that's tweaking our cycle time. We divide 2 pi by this coefficient. 2 pi divided by 2 is pi. So our period is 1 pi. And we could also just get that from the graph. If they did not give us this at all, we could say, well, we can see that here's the bottom of a valley. Here's the bottom of the next valley. So we went from a half pi radians to negative a half pi radians. To go from a negative a half to a positive half, we'd have to go 1 pi. For number 29, or 24, describe the relationship between the graphs of f and g. Consider amplitude, period, and shifts. And we haven't gotten to shifts yet. That'll be tomorrow. So let's see, amplitude. Are these graphs the same or different in amplitude? Well, remember, amplitude is the coefficient in front of the trig function. Here it's a 1 sine x, here it's a 1 sine of 3x. So the amplitude is the same. Amplitude for f of x and g of x is equal to 1. They have the same amplitude. Next it says to consider the period of the graph. Consider the period. Well, f of x is just sine x, and we know that f of x has a period of 2 pi. Period of 2 pi. What about the period of g of x? G of x. Well, remember, to find the period of the sine wave, we take 2 pi and divide it by the coefficient in front of x, which here in this example is 3. So f of x has a period of 2 pi, g of x has a period of 2/3 pi. Or we could write that as just 2/3 with the pi after it. But the pi is just with the numerator in that. It's exactly the same thing. And the last one. Now we actually do a little graph in here, so let me move this up. It says graph f and g on the same set of coordinate axes and include 2 full periods. So let me move this up here. The amplitude here is 2. This amplitude is a -1. And let's find the periods before we even set up the axes. So I'm going to do this upper one here in blue. The period is 2 pi divided by this coefficient. 2 pi divided by 2 is 1 pi. So f of x has a period of 1 pi. And we'll graph g of x in red. So the period of g of x is 2 pi divided by this coefficient, 4, or 1/2 pi. And we want to include 2 full periods on our graph. So let's see, here's our y-axis. Here's our x-axis. And we want to do 2 full periods. And our bigger amplitude, or our bigger period, is this 1 pi. So we at least want our graph to go out here to 2 pi. And let's see, half of that would be 1 pi. And then half of 1 pi would be 1/2 pi. And then here we would have 3/2 pi. And I'm not going to write them in there, but I'll use a different color here. These would be our quarter pi. Here's 1/4, 3/4, 1 1/4, 1 3/4. So let's see, we were going to do the first one here in blue. So we can see our amplitude is 2. So we know at the most we're going to, maybe not make it that high. Maybe right about here is going to be 2 and -2. And the period of this one will be pi radians, and it's the cosine function. Positive cosine functions will start up here on the top of a hill. For this graph, 1 pi later, we're going to be at the same height, at the top of another hill. In between these peaks will be a valley. In between 0 and pi radians is 1/2 pi. That's going to be the bottom of our valley. And we're going to cross the x-axis in between at these quarter pi radians. And we want to include 2 full periods. Let's graph the first period first here. So we're going to start at 1 at the top of a hill. We're going to go down here and cross at a quarter pi radians. Bottom out at the valley at 1/2 pi. And then head back up. Cross at 3/4 pi radians. And we're back up to the top of a hill. That was one period. We're going to do another full period. So we're here at the top of this hill. 1 pi later, we'll be back at the same spot. In between these peaks is a valley down here below 3/2 pi radians, and our x-intercepts are going to be these quarter pi radians in red. So we're at the top of this hill, cross the x-axis down to a valley, back up, cross the x-axis again, back up to a peak. So there in blue is the graph of 2 cos of 2x. We'll switch to red for this next one. And this is going to get a little tighter. Now our period is 1/2 pi. So we're going to do a full cycle by the time we cross 1/2 pi here. Ooh, this is going to get a little tight. And another tweak on this is it's negative cos. Positive cosine starts at the top of a hill. Negative cos starts at the bottom of a valley. So here we are going to start at -2. 1/2 pi later, we've completed a full cycle. Ooh, and this, it's at -1 cos. So actually we're not going to be down here at -2. We're going to be here at -1 and up to a high of +1. So here our cosine is going to start at the bottom of a valley. 1/2 pi later, we've completed a full cycle. So in between these valleys is going to be the top of a hill right about here. So this is going to go up, cross at an 1/8 pi, hit the top of a hill, come back down, cross the x-axis again, and bottom out at the valley at a 1/2 pi. That's one full cycle. And we at least want to do 2 full periods. So here we're at the bottom of a valley. Another 1/2 pi later, we're going to be at the bottom of another valley. Here are the bottom of our valleys. Right in between them is going to be the top of a hill. And we'll have x-intercepts in between. So bottom of a valley, up to our x-intercept, hit our hill, peak out, come back down, cross the x-axis, back down to the bottom of a valley. And what the heck, let's do another one. Here's another bottom of our valleys, top of our hill will be here, and connect the dots. And one more just for fun, why not? Here's our top of our hill, back up, hit our hill, back down, cross the x-axis, and finish. Let me get some of the garbage off these functions here. So 2 cos of 2x is a nice high one from 2 to -2, our peaks and our valleys. This 4 really scrunched the period up. The waves come quicker, up, down, up, down, up, down. You know, we're used to having 1 full cycle in 2 pi. For this function, we've had 4 full cycles. Top of a hill, back down. Top of a hill, back down, 2 full cycles. Another peak and valley, 3 cycles. Another peak and valley, 4 cycles when we usually have 1.